Hello,
go into
hello.
touch numbers, and it's just going to keep it in all of my classes. But it's kind of, I know where things are generally, so that's kind of nice.
Countdown. This is class 6
Oh my gosh.
of 6 more, right? 6, 5, 4, 3, 2. Why that wasn't, as a mathematician, that was pretty poorly described, but that's crazy. Crazy. So, let's talk about like what's out, what's due, when we want to do. So we don't have classes on Friday, no classes, right? Easter.
Do we have classes on Wednesday?
Sorry. At least this class. We have this class on Wednesday. And then we come back on Monday. So we do have Monday class. So there's a couple assignments out. There's the mass spring problem.
I have questions now.
Then I was going to take those next. Yep, awesome. That's a great. I'm glad to hear that. And then there's like the online, the web work exam. So I think that Vivian was suggesting that she's gonna kill me for saying this. She didn't. Vivian was suggesting that mass spring thing should be due a week from today. No, she wasn't. She just asked when it was due. Does that sound okay? Or do you want it sooner? You can turn it in sooner. If that really is your thing. Okay, cool. This is yes. All right. So that'll be due a week from today. I will take questions on it in just a second. The exam, the online exam, when was that due? Sunday. Yeah. I kind of like to keep that in place right now. I don't think that one shouldn't be too bad. So let's keep that exam due date a week from yesterday. Get that knocked out because you don't have to do it, right? It's like highly recommended for like a perfect addition to your grades. But okay, let's take questions about the mass spring stuff before we start Laplacing the hell out of things. I know. Ah, yes.
So, for part C, what was the first one?
Yeah, I'll probably have to remind myself what that was, but
So, can I just, I think you're asking for the time when we report past the equilibrium.
yes.
And so, that x equals 0 when you solve for third.
Yeah. Yes. Yeah. So which part was that? So that was
1C.
1C. Vivian was asked. I think here it says, what is the first time it crosses equilibrium? Lots of ways you could do that. I would recommend getting this into the phase amplitude form, or the yeah, right? Isn't that what I called it? Phase amplitude form, just to make life easier. Do I actually ask you to do that as part of the problem? No? Okay, cool. You don't have to. That makes life a little easier. Otherwise, you probably have to do it pretty numerically. But it says, when does it first cross equilibrium? So we've got some initial conditions. Probably it looks like that at the beginning. This is the time I want. And so we'll call it T1. That is achieved by just solving this. You'll get infinitely many solutions. So the one thing you have to be careful with here is because this is a sinusoidal thing, you will get infinitely many solutions. Pick the smallest positive one. So choose the smallest positive solution root. And that'll be the one you want. Does that make sense? Yeah, did you have anything else about that, or? Oh, I know. Okay, so Labina, you had questions first. Do you need time to get them?
I think I have question 2C.
Okay.
So
2C, is that what you said? Okay.
So we have a mass spring system modeled by x double prime plus 9x equals 4a cosine omega t.
Yeah.
Yeah. And it's x at 0 and x prime at 0 is 0.
Yes.
And a and omega are positive constants.
Yes.
Okay.
is a great problem. I love this problem, by the way, so.
So C says that the amplitude and the long-term sine together form an envelope for the short period sine,
Yes,
essentially governing its amplitude.
yes.
What is the equation for this envelope?
Do you want me to kind of address what to do there? Okay, cool. So, this problem, let's just talk about what this, I was hoping someone would ask, so thank you so much. Somebody was bound to ask about this because this problem's a little bit involved, but certainly very interesting. We have a mass spring system that has no initial displacement or velocity. So without this, if this were not here, the solution would be nothing, zero. There's nothing moving this thing. But then we put this weird, and it's written this way because it helps to have that 4A in front. The A governs the amplitude of the forcing, and this omega governs the frequency of the forcing. So again, it's something like this. You've got your mass spring, and down below here you've got some kind of thing. It's like my leaf blower / vacuum. So it pushes and pulls on this thing according to what omega is set at. So when you work this all through, for any particular omega, you'll get a solution that kind of looks like this. Yeah? So you see something like that. So what is happening is you've got this outer envelope on this thing. And that got really shitty there. So, yeah. That's terrible. But you've got this outer envelope, and I call that the long period sign, governing how this thing ebbs and flows. If you were listening to this, if this were a musical instrument, you would hear what are called beat tones. Who instrument people? Stringed instrument people in here? So, no. So one thing you could do on like a guitar is if you take one string that you want to tune and you take this other string and it's already at the tune you want, or maybe you hold a harmonic to get it to the frequency you want, and then you pluck this thing, and as this thing comes into tune with the note that's playing, or maybe you've got like a tuning fork here, and you hit that and it's resonating this frequency. As this thing comes into tune, you'll start to hear these beat tones. You hear whoom, whoom, whoom. It gets louder and quieter, and it's because this is happening as you get closer. The closer this omega gets to the natural frequency of this thing, which the natural frequency of this thing would be omega equals 3, right? Because that's, you've got 3 plus or minus 3i there. The closer you get to that, the longer that period gets on the outer envelope. So I know this isn't quite to your question yet, but it's stuff I gotta say. As you hit this note, what you see is, so like here's kind of the progression. You've got this outer envelope like this, and then you've got this other stuff inside here. As you get closer to the frequency, that envelope starts to get larger and longer. So the beats become louder and more spaced out. And then right as that omega approaches 3, the minute that omega goes to 3, your envelope becomes infinite. And all you see is what's called resonance at that time. So this is what you should be expecting when you're going through this thing. Your solutions, and you should plot these out in Desmos. I think I recommend that, right? You should be seeing this progression into this full-blown, like, kind of explosion in a way. So what am I talking about there? Well, you solve this thing, and you'll get some sine and cosine stuff over here. Use the formula I gave you to turn it into something like this. Some constant times a, did I have us do it as sines or cosines? Sines, cool, right. So you'll have like this omega 1t, and then a sine of omega 2t. Okay. So now what you're gonna do is view this part as the amplitude controller. So in other words, this is like, let's say here that this omega is smaller, so omega 1 is less than omega 2. Think about how that works. Any number that you have out in front of the sine function, let's actually talk about that for a minute, so maybe this will make more sense. If I had this, it's just basically a normal sine function of some frequency scaled to 7. So here the envelope is just y equals 7, y equals minus 7. If I did this, now I've got a normal sine function, but its amplitude is being governed by this exponential decay. So if I were to just plot this, e to the negative t, and then negative e to the negative t, all these oscillations have to live inside this envelope, because this literally governs the amplitude, the maximum amplitude. So you'd see something like this going on. And what we've got over here, and in this problem, is we've got a sine envelope over the whole thing. So what you need to do is break this down, figure out which one has the smaller number in front of the t. That'll be the longer period. So, right, because like if I had sine of t versus sine of 2t, what do those look like? Well, here's sine of t, and that's 2 pi. Here's sine of 2t. It's got half that period. So the one with the smaller number in front of the t is the longer period one. And think your period is 2 pi over omega. That's your period formula. So maybe that makes sense. So what I would recommend, let's actually do a specific example. Let's say I had done all the work, did the trig identity, and got this out. X of t equals 7 sine of 2t times sine of 3t. And I want to plot that. So I could go to Desmos, and I should go to Desmos to make sure that I'm thinking sanely about all of this. But the first thing I would do is plot just this. So when I say plot the envelope of the long period sine, it's this right here that I'm looking for. So that's just going to be a normal sine. And look, friends, if you want to sketch a sine, let me show you how to do it real quick. Here's how you sketch a sine. Every sine looks like this, right? So first you draw that. And then you just label everything around it. You set all your scales up to be perfect. So if I'm doing just 7 sine of 2t, where is this ending at of one period? Pi, yeah, just a pi. And then I take the halfway mark, right? And I got all that. And then you could get crazy in here with all the labelings that you want. And right, I gave you the formula over here, so you could just grab that off there. And that's really all I want. But it might be nice to actually sketch the negative of it as well, to show that the other sine of 3t needs to live inside there. But I guess, Labina, this is what I want for that problem, just the sketch like this of the long period sine. Does that help on that? Or did I not even address the question you were asking? Because I did just blab for a long time.
So, I think the question just wants us to find the equation.
Oh, even better. Yeah.
I think I got it, I just have to fix the periods, I think.
Okay. Sounds good to me. And so you feel okay about what needs to happen there?
Yeah.
It was more like a sanity check, sounds like. Okay, yeah, okay. Other questions on the mass spring thing? Second best day to ask about this is Wednesday. All right, so that's it. And Labina, you got anything else? Okay, Wednesday. There's always Wednesday. Alrighty, friends, let's get back to Laplace Town. Still, I'm not giving you an assignment on this yet, but I think like I should on Wednesday. So on Wednesday, I'm gonna give you a Laplace assignment, but you just got enough going on right now. I don't wanna overwhelm you. It's gonna probably overwhelm you no matter when I give it, so just a couple more days without it. Today is this. Yes, you have a handy dandy Laplace transform table in front of you. This has got all sorts of useful things in it. Some that some just seem kind of weird, but they're things that show up a lot when you're solving differential equations. You, by the end of the day, will be able to derive most of the things off of here. And then in the back, they give you a couple little bits of information. One is about a function called the gamma function, which you may or may not have had a lot of experience with. It's a pretty awesome function. It's defined in terms of an integral, but it's where the factorial comes from. It's literally just the super version of the factorial. Factorial is just a tiny little sliver of the gamma function. Yeah, and then hyperbolics, just giving you some tips on how you might find the Laplace transforms of those. So, I forgot where we left off. Let's see. I think last time we talked about Laplace transform of some basic things. So we know this. Yeah, didn't we do t to the n? And that was n factorial over s to the n plus 1. Cool. We have the Laplace transform of e to the kt, and that was 1 over s minus k. And we did Laplace transform of sine, which was, what goes on top without looking? Can you remember? What goes on top? K, yeah. It's not the s that matches sine. Thank you. So we got k over s squared plus k squared, and then this one is the cos. And this has the s on top, because it's not a sine. It's just maybe a stupid thing to keep saying. I think that's about all we did. And then we did a bigger example, right? So let me just make sure, and you can check in your notes, we did not do the Laplace transform of a power of t times something else, did we? I don't think we did. Did we get to where it's the derivative of the Laplace transform? Did we? We did? Maybe? Let's review. Let's go through it again. Yeah, what the hell. So, let's just talk about this really quick. If you have a t times something, let's go to the definition, and you can always go to the definition. Well, maybe I don't know about this. Let's take a look. Because this is kind of cool. I'm going to show you two properties today that are going to enable us to do a bunch of other things, and they're pretty straightforward, but we need the definition. Here's the thing you have to observe here. If I took the derivative with respect to s of that, what would I get? What's the derivative of that with respect to s? T times s. Yeah, exactly. Right, and let's think about why that is. dds of e to a function of s. It's the chain rule for exponentials. It's e to the, it's just you copy the e part over and then take the derivative of the exponent with respect to the variable of interest. So if I have this, and you have to understand this to see what's about to happen up there. But if I had this, then that's e to the negative st times the derivative with respect to s of negative st, and that's just negative t. Does that make sense? Yeah, Okay, so that is what I'm gonna go, and I'm gonna use this backwards. Notice that te to the negative st, which I see here, is actually negative derivative of e to the negative st. So this part here I'm gonna replace with negative dds of e to the negative st f of t dt. So just rewrote that part like that. Now notice the integral isn't, the integration variable's t, it's not s. This is a funky thing I'm about to do. If you were in like grad level math, you would have to justify this copiously, but it's okay for us that I can bring this outside. That to differentiate that inside here and then integrate is the same thing as integrating, then differentiating. And this is just the Laplace transform of f. So check it out. This equals negative Laplace transform of f of t. So multiplying by t on the inside before you transform is the same thing as transforming first, then differentiating with a sign in front. See this? Look, multiplying in here by t resulted in differentiating outside in Laplace space. Very strange thing. Now imagine that I had another power of t in there. Imagine I had t squared. Let me just kind of talk this through here real quick. So if I had t squared, how many derivatives do I need to get that t squared out there? So like, come down here, how many derivatives of this thing do I need to get a t squared here? Does this make sense? I'm saying two, yeah. So if I do this twice, in other words, let me just show you. If I take the second derivative with respect to s of e to the negative st, first derivative brings a negative t out in front, then I still got to do the next derivative. Next derivative brings another negative t out in front. So differentiating twice outside is the same thing as multiplying by t squared inside. And you can kind of see what I'm about to write up here, I think, if you just extrapolate from there, that this is n derivatives with a -1 to the n in front. So you got -1 to the n, nth derivative with respect to n of the Laplace transform of the original thing. This is the formula you want. And I don't know if that's on this sheet. I think it probably, is it?
30.
Oh, 13? 30? 30, thank you. Nice, yep, rule 30 right there. Thanks, kid. So let's do an example. Find the Laplace transform of te to the 3t. So that is going to be, here we have first power of t, so that's odd. Notice that the odd powers of t correspond to a negative in front, and the even powers are a positive in front. So I'm going to have that times the derivative of Laplace transform of e to the 3t. We've got the formula for that over there. So that's negative dds 1 over s minus 3. And when you take this derivative, however, do it your favorite way. Rewrite it as s minus 3 to the negative first, whatever. I'm going to let you actually finish this up. Keep our table up over here for easy access. Cool. So if you do this derivative, you should get, let's do all the parts separately. This is actually -1 over s minus 3 squared. And then the negative turns it into a positive. Any questions on that? We're gonna, it turns out we're gonna do that in a totally different way, that same thing in just a minute. Because it's part of the joy of Laplace transforms. It's cool things happen. Any clarification needed there, my friend? Yeah, Vivian, yes. Okay, yeah, you did have a question, okay, yeah.
How do you get from the ds to the negative?
Here to here?
Yeah.
Okay, so take that derivative of 1 over s minus 3. I'm glad you asked, because I'm sure you're not the only one. Oh, actually, I would write it like this and then chain rule. Yeah. Other things, yeah, good. Cool, one more law. And then once we have this law, we can do everything. So now, check it out. I can do t times e to a power. I can do t, powers of t times sine, powers of t times cosine. The one thing we don't know how to do right now is like e to the 2t sine of 3t. So we don't have multiples, or e to a power times this, one of these two. So let's just talk about that. Let's say I take the Laplace transform of e to the kt times a function f of t. And so go to the definition. Always go to the definition if you're unsure. Might take a little work, but it's not a painful definition. So this is integral. This one's like an observation away from being done. Get to where I'm at, see if you see what I did, and if not, let's chat about the exponent move I made there. So it's just like our exponent laws. I haven't done anything calculus-y at all, and I'm not going to. No calculus involved, pretty sweet. So this Laplace transform thing, let's just talk about this. This is a function of s. And you could write it like this, and we will a lot of the time. And in fact, on that table that you've got in front of you, they make this claim. Let's just call that a function of s with a capital F. The s is this variable right here. So I could say this. This is a function of something, and that something is that number that goes right there in the Laplace transform. So whatever's here, that's what goes here. What do we have there now? We have s minus k. So this is just the Laplace transform with s replaced by s minus k. So in other words, what I'm saying is that this is equal to Laplace transform of f of t with s replaced by s minus k. Multiplying by e to the kt says forget about that, just do the Laplace transform of that part, and then replace every s with an s minus k, and you've done that inside. I think examples are needed. This notation is kind of like mine, my own creation that I've developed over the years. This could also be a way to write it. Oh, let's do an example. Look, there's e to the kt times something. Oh, hell yeah. Let's do this a different way. So this is with, this is by rule star here. And then now we'll call this rule pound sign, and we'll do it that way. So by rule pound sign, this is the Laplace transform of t. And what is k here? It's 3, with s replaced by s minus 3. So this Laplace transform of t, well, that's just the power of t, so that's going to be 1 factorial over s squared. And then I'm going to replace s with s minus 3. And so my final answer is exactly the same thing we got the other way. It better be. If we're using legit techniques, we better get the same thing no matter how we get it. Those are equal. Yes, ma'am.
What happened to the, like what's the 2 notches next to the 1 that you put?
Oh, these are equal signs. Sorry, Ella. Yeah,
Oh.
they're not, yeah, how about this?
Okay,
Sorry. Yeah, I was even wondering, I was like, that looks weird, but I already started doing it. How about that?
I thought it was like primes or something. And I was
Yeah,
like,
I can see why. Yeah, no, it's good old equals. Vertical equals. Parallel equals. Let's do some practice. Let's practice both these rules together. So, we'll put that over here. And this is on your sheet, probably, Kid will find it before I find it. I gotta hurry up and try. I got it, number 29. Rule 29. Okay, so what is the Laplace transform of e to the negative t times sine of 3t? Let's give that a shot. What is S going to get replaced with here? I guess I didn't. What is it? Oh, yeah, Thomas.
Would it be s plus 1?
Indeed, it's S plus 1. Yeah, because it's going to be minus that number that's in front there. So that goes to S plus 1. Indeed. So if this thing up here is negative, you're going to have a plus. If this thing's positive, you'll have a minus down here. So now it's just a matter of knowing that formula. And that, you could just leave it like this. If you wanted, you'd be completely right. Yes, ma'am.
So for knowing like the s to s plus 1, like where, like why?
That's
where's that
this.
coming from?
That's this rule here. Take the Laplace if you have e to the kt times something, you do the something, and then you replace s with s minus the k. So here the k is minus 1. Does that make sense? Yeah? Cool. Other questions? Let me just do something here that we're going to undo in a minute. A lot of times I have to stop people from doing what I'm about to do, and normally I would stop you from doing this, but it's going to help to see this forward just a couple of times. I just expanded that out with a foil and combined everything. Why would I do that? Because when we're working with this stuff, we're going to need to go backwards, and you're going to see that. This is what you're going to be given, and you need to make it into that, and then work backwards up to here. So that's why I'm doing this. To get from here to here, you do a thing called completing the square, and we'll review that in just a minute. All right, see what I told, like, this class is so good for all your math. Like all that stuff you used to do, it comes back like crazy in this class. All those good skills. Let's do one more. Could you please do Laplace transform of t, cosine of t? What would that one be? In case you need the quotient rule and you forgot it. Yep, you need it. You can check yourself, you can check me with Formula 10. There, they just have A equals 1. I think we got it. Hey, can I talk? Anyone want to talk about any of that? Is that making sense? Come on in. Come on in. there's any questions there. Got one last one. What do you think the next one will be? What would you do next if you were doing this, leading this discussion? How many things would you put in the product? I would put it all together. So let's make our lives easy. Let's take that and just give it an e to the 7t out in front, t cosine of t. Let's do this one together. This could be a pain in the ass. This could be brutal. I would do this last. Even if I just had seen this problem, I would do this part last because this is just a sub at the end, right? We're going to replace s with s minus 7 at the end. So do this part first. So that's going to be Laplace transform of t cosine of t. And then we're going to replace s with s minus 7 after we're done with all that. Good news is we already did it. It's right there. So this is s squared minus 1 over s squared plus 1 quantity squared with s replaced by s minus 7. Now this is going to look hella messy, but we're going to do it anyway. We're not going to expand this one out because there's not much point in it. We could. It would be ugly, but that's our transform. That is a nasty looking thing. But all that matters is you see how I got it at this point. We're good? I'm seeing some nods. Ella, where do we need to talk? Ella, are you cool with the t cosine one?
Not really, I think that's fine.
Okay, well what's over here is troubling you? You cool with this?
Yes,
Okay.
it's the fourth step.
This, how did I get to here?
No, the one right
That's right here. Oh, okay.
between, like, I see why you use the s over s squared plus 1, but then you go to this next thing, like what?
How did I move from here to here? Or is it here to here?
Derivative to the one below it, yeah.
Oh, from here to there.
It's just because you took the derivative.
I used the quotient rule. So it's the derivative of the top, which is 1, times the bottom left alone. So, right, quotient rule, minus top left alone, that's the s, times the derivative of the bottom, which is 2s. So that's where that top came from. And then I just take the bottom and square it, because I'm literally just using that formula up there. So this is just, yeah, I could put here quotient rule, just to make that a little clearer. And then the negative just came along because of the formula. And then after that, are you cool with like the rest of it? Okay, awesome.
Yeah, I was just like behind and then I lost.
Yeah. Does that feel better?
Yeah.
Cool. So then you feel probably better about that guy there, because then I took this and said, well, this is just this transform with s replaced by s minus 7. So I'm using this because this is just like substitute at the end after you do everything. So that's what I did. I made the transition from here to here. This is like a little bit of note taking, right? Like I just moved this to like note to self, after you're done, do this. And then this we just computed. So I just took that answer from down there and replaced s with s minus 7. Does that help?
Yes.
You're welcome. Anything else? Okay, well, we won't do any more of that. Not right now, anyway. We're almost ready. We're almost ready to, I won't erase that yet, to do full-blown solving of some things. But I want to talk about the inverse transform really quick. So at this point now, you can do the Laplace transform of anything you're ever going to have to take the Laplace transform of, plus a lot of stuff that's on that sheet that I'll never ask you to do. But let's talk about the inverse transform, which is really just, do you understand the forward transform, and can you think about it backwards in many ways? So the inverse transform, L inverse, takes stuff in S space, so in other words, Laplace space, and puts it back into T space. And in the following way, I would say L inverse of something that is an S function is equal to some T function if and only if the Laplace transform of that is that. And so it's a very simple thing that I'm writing here, but it could be confusing, so let's maybe write a few examples out. There is one caveat. We're going to assume that our function here is as continuous as possible. So here, I'm just going to assume, for technical reasons, assume f is the most continuous version of itself. And I kind of like to leave that for right now and come back to it, like what that means. The good news, it's actually to ensure uniqueness. This is to ensure uniqueness of the output of this thing. So, if I asked you, what is L inverse of S over S squared plus 14? What is that? Well, what form is this? Trig form, right? It's one of the trig forms. Is it sine or cosine? It's cosine because it's got the S on top. What's K? This is K squared, right? So K is square root of 14. So I identify that. And then I work this backwards. This is going to be cosine of the square root of 14t. Right? So it'll become easier as you get more used to like even doing the forward version. Then you'll be able to identify, oh, that came from this. What about this one? What if I have L inverse of 1 over S squared plus 14? Right now, what form, which function is this referring to? Kind of. It's not quite there. You can't input new variables in. You can't insert variables, but you can put constants in. Oh, I should say this. This thing is linear. That's a big help. So that means if you do constants inside, you can have them out in front. You can bring things out front, inside. This is almost this sine of kt is k over s squared plus k squared. We almost have this. What am I missing? The k needs to be on top, right? That's got a k on top. So I'm going to insert that here. So I'm going to put on top, I'm going to leave a little space because I'm going to put a compensation out in front. That's L inverse of square root of 14 over s squared plus 14, and a 1 over square root of 14 out in front. You did this with integrals all the time back in the calc days. What a shock. That's just an integral, right? Like everything here is an integral. So the stuff you did with integrals keeps on cruising. So now I can do this. And this turns into 1 over square root of 14. This came from sine of square root of 14t. You'll never have to do that with the cosine. You'll definitely have to do it with, I think it really just the sine. I think the sine's the only one that you need to do that adjusting. Oh, wait. Let's do that one. Where do you get 1 over powers of s from? powers of t. What needs to be on top there for that to be a perfect transform? That would be so perfect. 6 factorial needs to be on top for that to be perfect. So I'm going to adjust. So this is 1 over 6 factorial. That's the compensation for just tossing numbers into something. And now that's t to the 7th, t to the 6th. So 1 over 6 factorial, t to the 6th. Yeah? Not too bad, right? It's like practicing the backwards helps you practice the forwards and vice versa. They really build each other. All right, well, what about, so now that we started handling more complicated things. Let's do the last most complicated one. So, what if I had L inverse of S over S squared plus 2S plus 5. Okay. So now it's getting real. I don't have any forms that look like that, right? We don't have anything that looks like that. But I'm going to work it into one of these forms. So first off, realize it's probably got to be one of these two things here, right? And you got the S on top already, right? So you can't just put it, you can't put an S on top and then a 1 over S out in front. You don't get to do that with variables, only constants. So watch this. I'm going to do a little rewrite, and I'm going to recognize that this thing in the bottom can be written as S squared, well, let's do it slow. S squared plus 2S, and then let's put a little plus over the 5 over here. What do I need to do to make this a perfect square? Do you remember how to complete the square? Take half this coefficient in front of the S, square it, and add it on. So I'm going to add on 1. And now I just added on 1, so this is a beautiful S plus 1 quantity squared. But I also added 1 in, so I need to subtract 1 as well. You can think of this, let me rewrite what I just did. This is L inverse of S over S plus 1 squared plus 4. You can think of this as I just borrowed a 1 from this and left the 4 off to the side. I just wanted to get this as a perfect square. Let me know if that makes sense. And I want to go slow because this is probably the most complicated of the things. What rule do you think might come in a reverse form? Yeah, Ella's totally looking at the right spot on the board. Like that subbing with an S minus K, that's what we need to do in reverse right now. So let's put up a nice inverse rule on how to do that. So we're just going to write this rule here in inverse form. And it helps to have a special version of it because it's hard to think about. For as many years as I've been teaching this is the part that I think people have the hardest time thinking about. So let's just make a little special rule that L inverse of, let's see, I got it written out here in a nice way. L inverse of something that's an S function is the same thing as e to the negative at on the outside, L inverse of the thing inside with S replaced by S minus A. So I'm going to write that out. So this is equal to e to the negative at, L inverse, I'm going to write it in English, of the thing to be transformed with S replaced by S minus A. What do I need to replace S with here to make it a perfect, To get this to just be s squared, what do I have to replace s with? To just get s squared down there. What would you put in here so that the whole thing just turned into s squared plus 4? What would you put in the s box? S minus 1. If I replace s with s minus 1, then this will just become s squared plus 4. So over here, so yeah, that's actually what we're going to do. I guess I can go use the damn rule now. Here, so let's write some things out. We want to replace s with s minus 1 so that s plus 1 becomes s squared. And actually becomes s minus 1 plus 1 equals s. That's what I meant, not s squared. So what I'm going to do is put out in front e to the negative t, Laplace inverse transform, and I'm going to replace every s with s minus 1, so the one on top as well. And then this down here, let's write it, so it becomes s minus 1 plus 4, that was squared. And so this becomes e to the, and I'm going to make sure to keep my equals all horizontal for the rest of my life, so they don't look like quotes and shit again. So this is s minus 1 over s squared plus 4. So let's just take our time. There's no rush here. Follow that. See if that is making sense to you. And I'm happy to walk, you know I'll walk through it like as much as we need. I will say everything same way 1,000 times. Okay, I'm gonna erase this. Hopefully you got that written down. I don't know, is this one on there? I better hurry up. I guess we don't really have inverse formulas on here. So it's on there, but in the forward form. Okay, so we're not done. So this is e to the negative t, L inverse of, now look at this, I'm gonna break this apart. This is s over s squared plus 4, minus 1 over s squared plus 4. And then I'm gonna use linearity and say that it's just the transform of this minus the transform of this. So let's write that out, e to the negative t, and you wouldn't probably do this on your own. You would just kind of write it all out and get it figured out, at least once you're good at this, and you will be. Linearity, let's break it apart. Can you finish this up for me, please? What does that turn into? We'll do one together. We'll do a couple of these together. This is really the last big thing we need to do. What'd you get? Oh yeah. That's it. Yeah, that was the part I was wondering if the number out in front. It's a tricky part. You get that secret, the half that needs to go out in front of that sign. Any questions on that? No? Let's do one more. Let's do one more together. This one I'll just let you do, and then we'll call it a day after this. Oh wait, I might have a couple written down in the notes. Yeah, I got some good ones. Okay. Oh, two more. This one's so good. Let's just do this one first. All right, so please, friends, L inverse of 3s plus 1 over s squared plus 9s plus 13. Let's make sure we complete the square first, right? So you see a quadratic in the bottom, complete the square to get it as something squared plus a constant. That's like first move. Should kind of work out pretty, I think, in a way. The completion of the square should be pretty. They're not always.
Just a rule to complete the square again.
What's that? I'm sorry.
What was the rule to?
Okay, let's talk about it. Let's complete the square together. So L inverse of 3s plus 1 over. So I'm going to pull the squared term and the linear term apart. So I've got that. I'll just pull. So what would I need to get this to be a perfect square? I would take, oh shit.
It's not 20 point. It's 20.25.
I thought, what was I fucking talking about? This isn't nice at all. Oh well, whatever. Yeah, so take half the nine. That's why you're like, do I not understand the rule? You do understand the rule. This problem is
Make it 8.
not pretty.
4.5 squared.
Yeah, so I'll say 9 halves. 9 half squares. So let's just call it 81 fourths. Minus 81 fourths. Shit, I'm starting to get scared. What is 81 fourths? This one, I don't want to do this one. I don't want to do this one.
81 divided by 4 is 20.
I don't want to do this. No, because this is going to take us into the next realm. Oh, let's just do it. God, like, it's not where I wanted to go, but let's go. Let's do. Should have what?
Should be negative 29 and
What?
I don't know what the whole thing was.
Wait, negative. Oh, this simplifies too. Oh, got you. Negative 29 fourths. Yeah, great. So this is equal to L inverse. I just want to, we just be brave. We'll just be brave. We're all together. So 9 halves squared plus minus 29 fourths. Okay. So what do I want to replace S with? S minus 9 halves. So I'm going to replace S with S minus 9 halves, and so an e to the negative 9 halves t comes out in front. I'm going to do that substitution. You got to do it on top. So S goes to S minus 9 halves plus 1. Notice that's 3 times that whole thing plus 1 over. Now at least that becomes nice. At least it's not like the last day of the week. I'll leave you with this. Let me know if that's looking okay. Because my next step is going to be to simplify the top. So this is e to the negative 9/2 t, L inverse of 3s still, and then minus 27/2 plus 1, so that's negative 25/2. Cool, thanks, that's good, I do need to hear that. I appreciate hearing those words of encouragement. Yeah? Here's what I didn't want to do today, which is about to happen. We need partial fractions to break this apart. Yeah. So the bottom is a difference, like a plus and a minus of the square root of this, right? So let's just do a little scratch over here. You'll be doing lots of scratch work with this stuff, but I'm going to take this, and this is s minus root 29/2 times s plus root 29/2. And I'm going to rewrite that as the sum of two fractions. And I need to figure out what a and b are. I'm sorry, I feel like feeling a new wind to come over me. We can fucking do this. Like, we're badass, right? We can do this. So then, this is the setup. Now multiply through by the denominator. So I'm going to get 3s minus 25/2 equals a times, this factor will cancel, plus b times this factor will cancel when I multiply through. Not so bad. That square root of 29 is not appealing to the eye, but it's just some shit we're writing on the board. It's no different than a 2. Okay, so now I gotta pick nice s values. So what I'm gonna do is I'm gonna pick s equals square root of 29, and this will die, and I'll know a. So here I'm gonna let s equal square root of 29/2, and then this left side becomes 3 square root of 29/2 minus 25/2. Okay, steady. And then this becomes square root of 29 times a. Right, because there's two of them. You get square root of 29/2 plus square root of 29/2, and that's dead. So a equals that divided by square root of 29. There we go. And then b, we're going to do the same thing to find b, but I'm going to let s equal negative root 29/2. And then the left side will become negative 3 root 29/2 minus 25/2 equals dead. And then negative square root of 29b. So b equals, now divide by that, and we're going to get 3/2 again, but this time plus 25 over 2 square root of 29. That's kind of nice. And we're just going to call those a and b, and now we're not going to keep writing those numbers. We're just going to say a equals this and b equals this, and let's carry this shit along. So this becomes e to the negative 9/2 t, L inverse of something a lot better. I'm going to rewrite it like this. And I'm going to keep the a and b on top, noting that we can come get them anytime we want. So it's going to be a over s minus root 29/2 plus b over s plus root 29/2. Oh, this isn't so bad. This isn't that bad. Yes. I don't think so. So this turns into e to the negative 9/2 t, and then what's the inverse of this? So it's going to be a, you pull the a out in front, imagine you have a 1 on top. What is L inverse of 1 over s minus k? So this is E, A times E to the square root of 29 halves T. And then this is just negative, right? So the K here is negative, that's why it looks like a plus. So plus B, E, negative root 29 halves T. And you know, that's fine. There's nothing wrong with this. I'm just gonna fucking write it out one more time and combine the exponents because there's very few things in this world that I try to keep tidy, as you know. But I'm just making this look the way I want it to. So this one's gonna be, that's nice. And then A and B is that shit. Where A and B are. Woo! Okay, that's enough. Thanks, everybody. We're gonna start solving stuff. Wednesday's like banner day in here. It's gonna be huge. Yeah. Hey, Chris, do you got just a minute after class? It's nothing bad. I just wanted, yeah. No, that's right. That's yeah, because you will get the omega in there like that. I think this looks legit.
I know.